Welcome back to Nocturnal Notions. Before we begin, if these journeys help you drift off, hit like and subscribe now while you're still awake. It means everything, and you won't want to remember to do it later. Tonight, we're leaving Earth behind. Not with rockets, not with calculations, just with stillness and the quiet willingness to look outward. Imagine a sky with no light pollution, no city glow on the horizon. Just you, lying flat on cool ground, staring straight up into a darkness so deep it almost pulls you in. The stars above you aren't decoration, they're distance. Each one a story, each one a question we've only begun to ask. As you settle in, picture that sky slowly expanding around you. The familiar constellations begin to drift apart. The moon shrinks behind you. The sun becomes one star among many. And then, even those fade. We've always looked up and wondered what's out there. Ancient civilizations built monuments aligned to stars they couldn't reach. Philosophers argued about whether the universe had edges. Scientists today still debate what came before the beginning. Tonight, we're not here to resolve any of that. We're simply going to travel. Calmly, slowly, the way light itself does. Let your breathing settle. Let the ground hold your weight. And allow the deep, ancient cosmos to carry you gently toward sleep. We begin at the very edge of what we can see. When you look at a distant galaxy, truly distant, millions or even billions of light years away, you are not seeing it as it is. You are seeing it as it was. The light leaving that galaxy began its journey long, long ago, crossing unimaginable distances through the void of space, traveling at 186,000 miles every single second, and yet still taking millions upon millions of years to finally reach your eyes. That light is, in every meaningful sense, a message. A message written in photons, sent from the ancient past, carried faithfully across the darkness until this very moment. Think about that for a moment. The image of that distant galaxy, that soft, faint smear of light, departed its source when the universe was far younger than it is today. When that light began its journey, there was no sun. There was no earth. There were no oceans, no mountains, no living things drawing breath in the dark. The universe was still in the early chapters of its story, still figuring out what it wanted to become. And yet here, right now, that light arrives. Patient and ancient and quiet. Those farthest galaxies we can detect, the ones sitting at the very edge of our observable universe, mark the earliest chapters of everything that has ever existed. When they formed, the universe was a very different place. It was hotter, far hotter, dense in a way that is almost impossible to imagine now. Matter was packed together tightly, the cosmos churning and roiling, full of energy and chaos and heat. The early universe was not the dark, still, peaceful expanse we think of tonight. It was loud, in the way that physics can be loud, full of radiation, full of collisions, full of rapid and violent change. And yet, out of that chaos, something extraordinary began to happen. Gravity, patient and relentless, began pulling hydrogen and helium together. Slowly at first. Then faster. Then, over millions of years, those great clouds of gas began to collapse inward, and the first stars began to ignite. And around those first stars, the first galaxies took shape. Now, something worth pausing on. When astronomers look at the deep sky, when they point a telescope at a patch of darkness that seems to contain absolutely nothing, they often find something remarkable waiting for them. If they stare long enough, If they allow the telescope to gather light over hours or even days, the darkness begins to fill. Faint smudges of light emerge from the black. Then more still. What looked like empty, featureless void slowly reveals itself to be full, absolutely saturated, with galaxies. This happened in a very famous way in 1995, when the Hubble Space Telescope was pointed at a tiny, carefully chosen patch of sky near the handle of the Big Dipper. The patch was minuscule, about the size of a grain of sand held at arm's length. Astronomers suspected it was empty. They pointed the telescope there anyway and allowed it to collect light for 10 consecutive days. What came back changed astronomy forever. In that single grain of sand-sized piece of sky, Hubble captured nearly 3,000 galaxies. 3,000 distinct islands of stars, each one containing billions of suns, each one separated from the others by unimaginable distances. This was the Hubble Deep Field, and it transformed the way we understand the universe. Because if one tiny patch of apparently empty sky holds 3,000 galaxies, then the full sky, every direction, every degree, every seemingly blank stretch of darkness above you, is crowded with them. Hundreds of billions of galaxies, scattered across the observable universe in every direction you could possibly look. The sky is not empty. It never was. It is full beyond any ordinary sense of the word full. And many of those galaxies, even the most distant ones, are enormous. It can be easy, looking at those faint smudges in a deep field image, to think of them as small things. Faint things. Fragile things. But they are not. Each one of those pale, barely visible smears of light contains billions of stars. In some cases, hundreds of billions. Spread across tens of thousands of light-years of space, held together by gravity, rotating slowly on timescales that make human civilization seem like the briefest flicker. The faintness is only a matter of distance. The light has simply grown thin from traveling so far. But the objects themselves, the galaxies, are vast. Ancient, immense in ways that resist easy comprehension. Here is another thought to carry with you as you rest. Many of the galaxies we see at great distances were already shining long before our sun ever existed. Before the Earth formed from a collapsing cloud of dust and gas. Before the oceans filled the basins of our young planet. Before the first microbes stirred in the primordial seas, and long before any living thing ever looked up at a night sky and wondered what was out there. Those galaxies were already old. Already full of stars that had lived and died. Already changed in ways that took billions of years to unfold. And their light, sent out before any of that happened here, is only now reaching us, arriving quietly, after a journey so long it almost erases the meaning of the word journey. The earliest galaxies, those ancient structures forming in the young universe, were built almost entirely from two elements: hydrogen and helium. That is nearly all there was, in the beginning. The universe had not yet had time to build anything more complex. The periodic table of elements that we know today, with its iron, its carbon, its oxygen, its silicon, all the rich chemistry that makes planets and oceans and living things possible, that table was almost completely empty. There was hydrogen. There was helium. And there was a universe full of potential, waiting. But the first stars, those massive, brilliant, burning giants that ignited inside the earliest galaxies, did something that would change everything. They fused hydrogen into helium, and helium into heavier elements still. Carbon, oxygen, nitrogen. silicon, iron. Deep inside the cores of those first great stars, the universe was building new ingredients, one fusion reaction at a time. And then those stars died. They did not die quietly. Stars of sufficient mass end their lives in explosions of extraordinary violence, supernovae, great blasts of light and energy that for a brief moment can outshine entire galaxies. And in dying, they scattered everything they had made. All those heavier elements, forged over millions of years in stellar cores, were hurled outward into space, into the gas clouds between stars, into the raw material of galaxies still forming. The cosmos was seeding itself, enriching itself, preparing, slowly and over vast timescales, for everything that was yet to come, including, eventually, the elements that would one day form you. And if you could travel back in time and look at those earliest galaxies up close, you might be surprised by what you found. We sometimes imagine galaxies as serene, elegant structures, graceful spirals, or smooth, glowing ellipses, hanging in the dark like works of art. But the ancient galaxies were nothing like that. They were messy, clumpy, irregular and turbulent, full of knots of intense star formation, lit up from within by blazing young stars being born at tremendous rates. Astronomers, when they first saw these objects clearly, sometimes called them hot messes, and the description fits. They were not orderly. They were not graceful. They were the chaotic, energetic, slightly overwhelming early drafts of the structures that would, over billions of years, settle into the more familiar galactic shapes we see closer to home. Order came later. Calm came later. The universe, like many things, needed time to find its shape. And one final thought, as you drift toward sleep. Some of the most distant galaxies we observe reach us looking stretched, or warped, or multiplied into strange arcs of light. They do not look quite like themselves. And the reason for this is one of the universe's most elegant tricks. Gravity bends light. Any mass, a star, a galaxy, a great cluster of galaxies, curves the space around it, and light traveling through that curved space follows the curve. When a massive object sits between us and a very distant galaxy, it acts like a lens. It bends the light from that far galaxy, distorting its image, sometimes stretching it into long arcs, sometimes splitting it into multiple copies of itself, sometimes magnifying it so that we can see it far more clearly than we otherwise could. These natural lenses, formed by gravity itself, allow us to peer even deeper into the universe's past. They are the cosmos offering us a gift, a longer view, a clearer signal, a slightly better look at what was there in the very beginning. So tonight, as you close your eyes, know this. The darkness above you is not empty. It is full of light too old and too faint for your eyes to see. Full of galaxies that were born before your sun existed, forged from the simplest ingredients, built by gravity and chaos and time. Full of ancient starlight that has crossed the universe to be here, in this moment, while you rest. You are surrounded by the deep past. And it is very, very quiet out there. If you are still awake, that is perfectly fine. Let your body stay heavy, let your breathing stay slow, and allow these words to carry you a little further out into the universe. And if sleep has already found you once tonight, perhaps it will find you again, gently, without effort, like it always does in the end. We left off at the edges of what is visible. At ancient galaxies, warped and stretched by the gravity of everything that lies between them and us. Tonight, we follow that thread a little further. We go deeper. We go earlier, and we meet the extraordinary instruments that humanity has built to listen for the faintest signals the universe has to offer. We talked, at the end of our last journey, about gravitational lensing, the way that massive objects bend light, curving it around them as it passes. And we touched on how this natural phenomenon can distort the images of distant galaxies, stretching them into arcs, warping their shapes, transforming them into something unfamiliar. But there is another side to gravitational lensing that is worth dwelling on. Because lensing does not only distort, it also amplifies. When a massive galaxy or cluster of galaxies sits between us and something even further away, it does not merely bend the light from that distant object, it concentrates it. It gathers light that would otherwise spread out and weaken across billions of light years, and it focuses it, the way a glass lens focuses sunlight onto a single bright point. The result is that a galaxy which would otherwise be far too faint for any telescope to detect, a whisper of light, nearly lost in the darkness, becomes visible. Magnified. Bright enough to study. Gravitational lensing, in this sense, is one of the universe's great acts of generosity. It hands us a longer reach than we have any right to expect. It takes galaxies from the very edge of the observable universe and brings them just a little closer, just a little clearer, just enough to learn something from. And when the geometry is exactly right, when a distant galaxy, a massive lens, and our telescope align almost perfectly along a single line, lensing produces something genuinely beautiful. Arcs of light. Sometimes nearly complete circles, glowing rings of a galaxy's image bent all the way around the mass that is lensing it. These are called Einstein rings, named for the physicist who first predicted that gravity would bend light in precisely this way. They appear in deep space images as faint, luminous loops, ghostly halos surrounding the dark heart of whatever massive object is doing the bending. Sometimes lensing produces not a ring but several separate images of the same galaxy, scattered around the lens like reflections in a curved mirror. 4 images, or 3, or 2, each one a copy of the same distant object, each one showing it from a slightly different angle, carrying light that took a slightly different path to reach us. And because those paths are different lengths, the light from each copy arrives at a slightly different time. This is one of the stranger, quieter wonders of gravitational lensing. When something dramatic happens inside a distant lensed galaxy, a star exploding, perhaps, or a burst of intense energy from the galaxy's core, astronomers who are watching might see that event more than once. The first image delivers the light from one path. Then, days or weeks or even years later, the same event arrives again through a second path, slightly longer, slightly delayed. And then perhaps a third time, through a third path. The same cosmic moment, replayed. The universe offering an encore. It is, in a way, the closest thing physics has to a time machine. Not the kind that lets you change anything, just the kind that lets you watch. Now, there is something else worth understanding about the light from very distant galaxies. Something that has to do with color, and with the nature of the expanding universe itself. As the universe expands, it does not simply push galaxies further apart the way a hand might push objects across a table. Space itself is stretching. And as it stretches, it carries light along with it, and stretches that light too. Light, as it travels, has a wavelength. Wavelength determines color. Short wavelengths appear blue or violet. Long wavelengths appear red or orange. And when the universe stretches light over billions of light years of travel, it pulls those wavelengths longer, shifting them toward the red end of the spectrum, and then beyond it entirely, into infrared light that human eyes cannot see at all. This is called redshift. And the further away a galaxy is, the more its light has been stretched, and the more deeply red, and eventually infrared, it appears. The most ancient galaxies, the ones whose light has been traveling the longest, have been so thoroughly redshifted that almost none of their light remains in the visible spectrum at all. They glow, if you can call it that, in deep infrared. In wavelengths of light that pass through ordinary cameras without leaving any trace. To see them, you need a different kind of eye. The James Webb Space Telescope was built, in large part, to be that different kind of eye. Launched on Christmas Day 2021 and positioned nearly 1 million miles from Earth, Webb is an infrared telescope designed specifically to detect the long, stretched wavelengths of light that the universe's oldest galaxies emit. Its mirror, made of gold-coated beryllium segments and spanning over 21 feet across, gathers infrared light with extraordinary sensitivity. Its instruments cool themselves to temperatures just a few degrees above absolute zero, because infrared detectors must be cold to work, otherwise the faint signal of ancient starlight would be drowned out by the warmth of the telescope itself. Webb is, in every sense, a machine built for patience. For listening to the quietest signals. For seeing the things that have been there all along, invisible to every instrument that came before. And what Webb has seen, since it began returning science data, has been remarkable. It has detected galaxies whose light left them only a few 100 million years after the Big Bang, when the universe was less than 5% of its current age. Galaxies from a time so early that the cosmos was still, in many ways, in its infancy. Still assembling the first large structures from its primordial fog of hydrogen and helium. The record has been pushed further still. Recent observations have identified galaxy candidates seen at a redshift of around 14, meaning their light left them approximately 280 million years after the Big Bang. 280 million years sounds like a long time. But the universe is nearly 14 billion years old. In those terms, these galaxies are from the very first breath of cosmic history. The very first whisper of structure in an almost structureless universe. But Webb has not only pushed the boundary of how far back we can see. It has also raised some genuinely puzzling questions. Some of the early galaxies Webb has found are far brighter and far more massive than our current theories of galaxy formation would predict. According to our best models of how galaxies grow, slowly, gradually, built up over hundreds of millions of years from merging clouds of gas and colliding smaller structures, certain galaxies simply should not be as large or as luminous as they appear at such early times. And yet there they are. Bright. Massive, fully formed, or nearly so, far earlier than they have any right to be. Astronomers are not in a panic about this. Science rarely works that way, but they are paying close attention. Because these galaxies are telling us something. Perhaps our models of early star formation are missing a piece. Perhaps galaxies in the early universe could grow faster than we thought, under conditions that no longer exist. Perhaps there is something about the first billion years of cosmic history that we have not yet understood. The universe, as always, is not entirely willing to be fully known. But it is generous with clues. And then there is this. Something a little unexpected and quietly lovely. Among the ancient galaxies that Webb and other telescopes have observed at great distances, from times when the universe was young and chaotic and full of turbulence, some of them show spiral structure. orderly, sweeping spiral arms, like the ones we see in galaxies much closer to home, in a much more mature and settled universe. This was not entirely expected. Spiral galaxies take time to form. They require a kind of gravitational settling, a gradual organization of gas and stars into rotating disk structures with arms that trail behind like water in a slow current. The early universe was thought to be too wild, too young, too messy for that kind of order. And yet the spirals are there, emerging earlier in cosmic time than the models suggested, suggesting that the universe can find order sooner than we gave it credit for. That even in chaos, structure has a way of asserting itself, quietly, patiently, without any particular hurry. But not everything in the early universe was finding its shape so gracefully. Many young galaxies, observed at great distances, are clumpy, visibly irregular, lit up in bright, dense knots of intense star formation. These knots are enormous by any local standard. In our own cosmic neighborhood, star-forming regions, clouds of gas and dust where new stars are being born, are impressive but contained. The Orion Nebula, one of the closest and most active stellar nurseries to our own solar system, spans only a few dozen light-years. The clumps in early galaxies can be thousands of light-years across. Blazing regions of stellar birth, operating at intensities that have no real equivalent in the universe today. Producing new stars at rates that seem almost reckless by modern standards. In the young universe, everything was more urgent, more abundant, more extreme, as if the cosmos, newly formed and full of raw material, was trying to do everything at once. And so we arrive here, in a universe that is ancient and expanding, full of galaxies seen through lenses of gravity, shifted into infrared light, captured by instruments of almost unimaginable sensitivity, full of surprises that keep quiet for billions of years and then reveal themselves all at once to a telescope floating cold and still in the dark. There is so much out there, so much that has been, and so much that is still being slowly understood. But right now, none of it requires anything from you. The telescopes are watching. The universe is continuing its long, unhurried story. And you are here, warm and still, with nothing left to do tonight but rest. Let your thoughts loosen. Let the distances dissolve. Let the ancient light fall softly around you like the quietest kind of snow. Settle in a little deeper. Let whatever tension remains in your shoulders simply fall away. Let your breathing find its own slow rhythm, easy and unhurried, and allow yourself to be carried once again into the deep universe, further along in its story now, further along in time, into a cosmos that has grown a little older, a little more complex, and a little more interesting than the one we left behind. Because now things are beginning to move. In the very early universe, galaxies were assembling themselves from raw material, clouds of hydrogen and helium collapsing under gravity, stars igniting in clumpy, turbulent bursts, structure emerging slowly from what had been, not so long before in cosmic terms, a nearly featureless expanse. But as the universe aged, something else began to happen. Those early galaxies, and the dark matter halos they were embedded in, were not simply floating apart from one another in peaceful isolation. They were close together. Far closer, on average, than galaxies tend to be today. And gravity, always working, always patient, was pulling them toward each other. The early universe was full of collisions. Not collisions in the way we might imagine, sudden, violent, over in an instant. Galaxy mergers operate on timescales so vast that the word collision almost loses its meaning. A typical merger between two large galaxies can take hundreds of millions of years from first approach to final coalescence. Two galaxies drift toward each other, feel each other's gravity, swing past in a long curving arc, pull back, swing past again, and eventually, slowly, over immense stretches of time, spiral together into one. Seen from a vast distance and sped up enormously, it would look like a dance. A slow, gravitational waltz between enormous partners, each one distorting the other, pulling on the other, reshaping the other with every pass. And these encounters were not quiet. When two gas-rich galaxies collide, the stars within them, counterintuitively, almost never actually collide with each other. Stars are so small relative to the distances between them that even two entire galaxies can pass through each other without a single stellar collision occurring. But the gas is different. Gas clouds meet, compress, slam together, and in doing so they trigger something spectacular. Star formation ignites across the merging system at an extraordinary rate. What is called a starburst, a brief, blazing episode of stellar birth that can produce more new stars in a single million years than a quiet galaxy might form in a billion. The merging galaxies light up from within, blazing with the blue-white fire of countless young massive stars, burning furiously and brilliantly. It cannot last. Starbursts consume their fuel rapidly. The gas that feeds them is used up, or blown away by the energy of the stars themselves. But while they burn, they are among the most luminous events in the universe, visible across distances that challenge comprehension, signals of violence and creation happening simultaneously, inseparably, in the hearts of colliding worlds. And as galaxies collide, they leave marks on each other. Signatures of the encounter, written in stars. The gravity of one galaxy pulls on the stars of the other, and not uniformly. Different parts of the galaxy feel the gravitational tug differently, and the result is that stars are stretched out, drawn away from the main body of the galaxy in long, curving streamers. These are called tidal tails, and they can be extraordinary structures, ribbons of stars and gas that trail out from a merging pair for hundreds of thousands of light-years in every direction. In deep images of colliding galaxies, these tails are visible as faint, delicate arcs sweeping away from the bright cores of the merging systems. They look almost gentle, given the violence that produced them. Like the wake left behind by something enormous moving slowly through still water. But tidal tails are not merely beautiful wreckage. They are also, sometimes, nurseries. Within those long streamers of stars and gas flung out by galactic collisions, the raw material of new galaxies can sometimes find each other again. Gas clouds in the tidal tail collapse under their own gravity. Stars begin to form. And slowly, in the debris of a collision between two large galaxies, small new galaxies take shape, dwarf galaxies, born not from pristine primordial material but from recycled matter, torn from larger structures and given a second life in the quiet outskirts of a collision. There is something quietly moving about this. Out of an encounter that reshapes two ancient galaxies, something new is born. The universe finding a use for everything, wasting nothing, turning disruption into creation. Dwarf galaxies, small, often irregular, containing millions to perhaps a few billion stars rather than the hundreds of billions found in large spirals, are more than just byproducts of collisions. They are, in a very real sense, the fundamental building blocks of the larger structures we see around us. Our current understanding of how the universe builds structure, a framework called hierarchical assembly, holds that large galaxies grow primarily by accumulating smaller ones. Not all at once, but steadily, over billions of years. Dwarf galaxies fall inward, pulled by the gravity of their larger neighbors, and are gradually absorbed. Their stars are added to the growing system. Their gas, if they have any, fuels new star formation in the host galaxy. Their dark matter halos merge with the larger halo surrounding the host. The large spirals and ellipticals we see today are, in a sense, the accumulated product of countless such meals. Built up patiently, one small galaxy at a time, over the full span of cosmic history. And some of those meals are still in progress. Even now, in the present-day universe, dwarf galaxies are being tidally disrupted, pulled apart by the gravity of larger systems they have wandered too close to. As they are torn apart, their stars are stripped away in long, thin streams, wrapping around the larger galaxy in faint ribbons of disrupted light. Our own Milky Way is surrounded by several such streams, thin arcs of stars left behind by dwarf galaxies that wandered too close and were gradually dismantled over hundreds of millions of years. The Sagittarius dwarf galaxy, for instance, has been orbiting and slowly merging with the Milky Way for billions of years, leaving a great looping stream of stars that traces its path around our galaxy like a faded scar. These stellar streams are records, fossils of ancient interactions, preserved in the positions and motions of stars, readable by astronomers who know how to look. Over time, the accumulated evidence of all these mergers, the absorbed dwarfs, the disrupted companions, the tidal debris from ancient encounters, builds up around galaxies in what are called stellar halos. Faint, diffuse clouds of stars extending far beyond the bright disk or body of the galaxy, full of old stars on randomized orbits that betray their origins as captured or disrupted satellites. These halos are ghostly things, too faint to see easily, requiring long exposures and careful image processing to reveal. But they are there, wrapped around galaxies like a dim and ancient memory of every encounter the galaxy has had across its lifetime. Every loop of stars, every faint shell, every thin stream curling through the halo tells a story about a smaller galaxy that no longer exists, consumed long ago, its identity dissolved into the larger structure, remembered only in the orbits of its scattered stars. Now, not all galactic growth produces the graceful spirals that most people picture when they imagine a galaxy. There is another class of galaxy, enormous, smooth, featureless, that tells a different story about what repeated merging can do. Giant elliptical galaxies. They contain some of the most stars of any galaxies in the universe, often hundreds of billions, sometimes trillions. But they are not disks. They have no spiral arms, no rotation to speak of, no grand organized structure. They are, instead, smooth spheroidal swarms, their stars moving in orbits that point in every direction, randomized and blended together into a kind of stellar cloud. This is what repeated merging does. When two disk galaxies collide and merge, the orderly rotational structure of both disks is disrupted. Stars that were moving in one organized direction are flung onto new trajectories. The two rotation patterns compete and partially cancel each other out. What is left, after the merger is complete, is not a new disk but a smooth, pressure-supported ellipsoid, a galaxy that has traded elegance for size, geometry for mass. Giant ellipticals sit at the centers of massive galaxy clusters, where mergers have been most common and most dramatic. They are, in a sense, the endpoints of a long history of galactic consumption. The final form of structures that have been growing and merging since the earliest times. But growing does not always mean thriving. And here is one of the quieter, sadder stories in the lives of galaxies. In dense environments, galaxy clusters, where hundreds or thousands of galaxies are packed into a relatively small region of space, the space between galaxies is not empty. It is filled with hot, diffuse plasma, gas heated to tens of millions of degrees by the gravitational energy of the cluster. And as a galaxy moves through this hot plasma, the plasma pushes back. It strips the galaxy's own gas away, sweeping it out from between the stars, removing the raw material that the galaxy needs to form new stars. This process, called ram pressure stripping, can shut down star formation in a galaxy within a relatively short time. The galaxy's gas is simply removed, blown away by the pressure of the surrounding medium. Without gas, no new stars can form. The existing stars age and are not replaced. The young, hot, blue stars die off, and only the old, cool, red stars remain. A galaxy that was once blue with the light of active star formation gradually reddens, dims, and quiets. It becomes what astronomers call a quenched galaxy, still intact, still full of stars, but no longer growing in the way that living galaxies grow. And yet, even a quenched galaxy is not entirely finished. A galaxy can stop forming stars and still, quietly, continue to grow. Not by creating anything new, but by accumulating. Small companion galaxies, old, gas-poor, themselves no longer forming stars, occasionally drift close enough to be captured. They merge in, slowly and gently, adding their old stars to the outer regions of the host. No fireworks. No starburst. No tidal tales of any consequence. Just a quiet, gradual accumulation of stellar mass, merger by minor merger, over billions of years. It is, in its way, one of the most peaceful things a galaxy can do. Growing old gracefully, adding to itself without drama, becoming, slowly and without fuss, a little larger than it was. And so the universe continues its long work. Galaxies colliding and merging, star formation blazing and fading, small structures feeding large ones, large structures growing old and quiet, the whole vast ensemble slowly evolving, rearranging itself across timescales that have no human equivalent, moving toward configurations that will not be fully in place for billions of years yet to come. All of it happening right now, out there in the dark. Unhurried. Immense. Indifferent to the hour. While you rest. Let it all continue without you for a while. Let the galaxies do their slow, patient work. And let yourself sink just a little further into the quiet. And some of those meals are still in progress. Even now, in the present-day universe, dwarf galaxies are being tidally disrupted, pulled apart by the gravity of larger systems they have wandered too close to. As they are torn apart, their stars are stripped away in long, thin streams, wrapping around the larger galaxy in faint ribbons of disrupted light. Our own Milky Way is surrounded by several such streams, thin arcs of stars left behind by dwarf galaxies that wandered too close and were gradually dismantled over hundreds of millions of years. The Sagittarius dwarf galaxy, for instance, has been orbiting and slowly merging with the Milky Way for billions of years, leaving a great looping stream of stars that traces its path around our galaxy like a faded scar. These stellar streams are records. Fossils of ancient interactions, preserved in the positions and motions of stars, readable by astronomers who know how to look. Over time, the accumulated evidence of all these mergers, the absorbed dwarfs, the disrupted companions, the tidal debris from ancient encounters, builds up around galaxies in what are called stellar halos. Faint, diffuse clouds of stars extending far beyond the bright disk or body of the galaxy, full of old stars on randomized orbits that betray their origins as captured or disrupted satellites. These halos are ghostly things, too faint to see easily, requiring long exposures and careful image processing to reveal. But they are there, wrapped around galaxies like a dim and ancient memory of every encounter the galaxy has had across its lifetime. Every loop of stars, every faint shell, every thin stream curling through the halo tells a story about a smaller galaxy that no longer exists, consumed long ago, its identity dissolved into the larger structure, remembered only in the orbits of its scattered stars. Now, not all galactic growth produces the graceful spirals that most people picture when they imagine a galaxy. There is another class of galaxy, enormous, smooth, featureless, that tells a different story about what repeated merging can do. Giant elliptical galaxies. They contain some of the most stars of any galaxies in the universe, often hundreds of billions, sometimes trillions. But they are not disks. They have no spiral arms, no rotation to speak of, no grand organized structure. They are, instead, smooth spheroidal swarms, their stars moving in orbits that point in every direction, randomized and blended together into a kind of stellar cloud. This is what repeated merging does. When two disk galaxies collide and merge, the orderly rotational structure of both disks is disrupted. Stars that were moving in one organized direction are flung onto new trajectories. The two rotation patterns compete and partially cancel each other out. What is left, after the merger is complete, is not a new disk but a smooth, pressure-supported ellipsoid, a galaxy that has traded elegance for size, geometry for mass. Giant ellipticals sit at the centers of massive galaxy clusters, where mergers have been most common and most dramatic. They are, in a sense, the endpoints of a long history of galactic consumption. The final form of structures that have been growing and merging since the earliest times. But growing does not always mean thriving. And here is one of the quieter, sadder stories in the lives of galaxies. In dense environments, galaxy clusters, where hundreds or thousands of galaxies are packed into a relatively small region of space, the space between galaxies is not empty. It is filled with hot, diffuse plasma, gas heated to tens of millions of degrees by the gravitational energy of the cluster. And as a galaxy moves through this hot plasma, the plasma pushes back. It strips the galaxy's own gas away, sweeping it out from between the stars, removing the raw material that the galaxy needs to form new stars. This process, called ram pressure stripping, can shut down star formation in a galaxy within a relatively short time. The galaxy's gas is simply removed, blown away by the pressure of the surrounding medium. Without gas, no new stars can form. The existing stars age and are not replaced. The young, hot, blue stars die off, and only the old, cool, red stars remain. A galaxy that was once blue with the light of active star formation gradually reddens, dims, and quiets. It becomes what astronomers call a quenched galaxy, still intact, still full of stars, but no longer growing in the way that living galaxies grow. And yet, even a quenched galaxy is not entirely finished. A galaxy can stop forming stars and still, quietly, continue to grow. Not by creating anything new, but by accumulating. Small companion galaxies, old, gas-poor, themselves no longer forming stars, occasionally drift close enough to be captured. They merge in, slowly and gently, adding their old stars to the outer regions of the host. No fireworks. No starburst. No tidal tales of any consequence. Just a quiet, gradual accumulation of stellar mass, merger by minor merger, over billions of years. It is, in its way, one of the most peaceful things a galaxy can do. Growing old gracefully, adding to itself without drama, becoming, slowly and without fuss, a little larger than it was. And so the universe continues its long work. Galaxies colliding and merging, star formation blazing and fading, small structures feeding large ones, large structures growing old and quiet, the whole vast ensemble slowly evolving, rearranging itself across timescales that have no human equivalent, moving toward configurations that will not be fully in place for billions of years yet to come. All of it happening right now, out there in the dark. Unhurried. Immense. Indifferent to the hour. While you rest. Let it all continue without you for a while. Let the galaxies do their slow, patient work. And let yourself sink just a little further into the quiet. If you are still here, still drifting, that is exactly where you should be. There is nothing to solve tonight, nothing to plan, nothing to hold on to. Just this, the soft, steady unfolding of the universe, one layer at a time, while the world outside goes dark and still. We have traveled far already. We have watched the first galaxies ignite from primordial gas. We have seen light bend around invisible masses and arrive at our telescopes ancient and reddened from its journey. We have watched galaxies collide in slow motion, merge, and grow. And now we go deeper still, into the hidden hearts of galaxies, where the most extreme objects in the known universe quietly feed, and burn, and roar. At the center of nearly every large galaxy in the universe, there sits a supermassive black hole. Not the stellar mass black holes formed when individual stars collapse. Those are measured in units of solar masses, tens or hundreds of times the mass of our Sun. Supermassive black holes are something else entirely. Millions of times the mass of the Sun. Billions, in the most extreme cases. Compressed into a region of space smaller than our solar system, hidden behind an event horizon from which nothing, not matter, not light, not information of any kind, can ever escape. For most of a galaxy's life, its central black hole sits quietly. It has already consumed what was available to it, and without fresh material falling inward, it produces no particular signal. The Milky Way's own central black hole, a relatively modest 4 million solar masses, is like this now. Present, massive, but essentially dormant. But when gas falls inward toward a supermassive black hole in large quantities, something extraordinary happens. The gas does not fall straight in. It spirals, forming what is called an accretion disk, a flattened, rotating structure of infalling material that heats up as it compresses, reaching temperatures of millions of degrees. At those temperatures, the disk blazes with radiation across the entire electromagnetic spectrum, visible light, ultraviolet, X-rays, pouring energy outward in quantities that stagger the imagination. The result is called a quasar. And a quasar is not a subtle thing. A single quasar, at its peak, can outshine every star in its host galaxy combined, outshine hundreds of billions of suns, by a factor of hundreds or even thousands. They are the brightest sustained sources of light in the universe. so luminous that they were visible to early radio and optical telescopes as apparently stellar points of light, mistaken at first for unusual stars within our own galaxy, before their true nature and their true distances were understood. They are not stars. They are the lit fuses of feeding black holes, burning at the centers of distant galaxies, blazing across billions of light-years of space. But quasars are more than just the universe's most powerful light sources. They are also, in a quieter and more subtle way, some of our most useful tools for understanding what lies between galaxies. The space between galaxies is not truly empty. It is threaded with diffuse gas, hydrogen and other elements, thinly spread across the vast intergalactic medium. This gas is almost impossible to detect directly. It produces no particular light of its own. It simply exists, invisibly, in the enormous voids between galactic structures. But when a quasar's brilliant light passes through this gas on its way to our telescopes, the gas leaves its mark. Specific wavelengths of the quasar's light are absorbed by atoms in the intervening gas, each element absorbing its own characteristic wavelengths, leaving tiny notches in the quasar's spectrum like bites taken from a smooth curve. Astronomers, reading these absorption features, can reconstruct an inventory of everything the quasar's light passed through on its journey. The composition of intergalactic gas clouds, their temperature, their density, even their distance, all of it encoded in the small, precise fingerprints they leave in the spectrum of a distant quasar's light. The quasar becomes a backlight, and the universe between us and it becomes, suddenly, readable. Active black holes do more than simply shine, however. In many cases, they also launch. Powerful magnetic fields threading through the accretion disk can channel some of the infalling material into narrow, focused jets, streams of plasma accelerated to nearly the speed of light and fired outward along the black hole's rotational axis. These jets can travel extraordinary distances, not just through the host galaxy, but far beyond it, extending hundreds of thousands or even millions of light-years into intergalactic space. Where these jets encounter the diffuse gas of the intergalactic medium, they push it aside, carving great cavities and lobes of disturbed material that can persist for hundreds of millions of years. Radio telescopes reveal these structures as enormous bubbles and plumes surrounding the cores of active galaxies, monuments to the energy output of a single feeding black hole, written large in the fabric of space around it. They are among the largest coherent structures produced by any single object in the universe. Carved by something no larger than our solar system, extending across distances that would take light millions of years to cross. And those jets, along with the fierce radiation winds driven by the quasar itself, do something else of profound importance. They heat the gas surrounding the galaxy. The enormous energy output of an active black hole floods outward through the host galaxy and beyond, warming the gas that would otherwise cool, condense, and eventually collapse into new stars. In a real sense, a feeding black hole can regulate its own galaxy's growth. As it feeds and blazes, it heats the surrounding medium, preventing fresh gas from falling in and forming stars. Star formation slows. Eventually, perhaps, the gas supply to the black hole itself is cut off. The quasar fades. The galaxy quiets. It is a feedback loop operating across tens of thousands of light-years, a black hole no larger than a solar system, influencing the fate of hundreds of billions of stars. The smallest scales of physics connected to the largest scales of galactic structure through nothing more than energy and gas and gravity. But not all of this drama is visible to the eye. Some of it, a great deal of it, in fact, is hidden. Dust is everywhere in galaxies. Fine particles of carbon and silicate, produced in the atmospheres of aging stars and scattered through the interstellar medium, absorb and scatter visible light with great efficiency. A galaxy with a powerful active nucleus buried behind a thick concentration of dust may look, to an ordinary optical telescope, surprisingly calm. The dust absorbs the blazing radiation from within and re-emits it at much longer, cooler wavelengths, in the infrared, where ordinary cameras cannot see it. This means that some of the most energetic, most active galaxies in the universe are hiding in plain sight. Looking quiet. Looking faint. Looking, to visible light observations, like nothing in particular. Infrared telescopes pierce this veil. They detect the reprocessed heat radiation pouring out from behind the dust, revealing the true luminosity within. And what they find, in many cases, is a galaxy blazing with activity, star formation operating at ferocious rates, or an active nucleus burning at full intensity, entirely concealed behind a curtain of dust that visible light cannot penetrate. Star formation itself can hide in the same way. A distant galaxy might appear, in an optical image, as a faint and unimpressive object, dim, redshifted, unremarkable. But in the infrared, it can reveal itself as one of the most intensely star-forming objects in the universe. Dusty starburst galaxies, as they are called, can produce new stars at rates hundreds or thousands of times higher than a typical quiet galaxy, all of it hidden from visible light, all of it radiating its energy in the infrared and at even longer wavelengths. And at radio and millimeter wavelengths, something else becomes visible entirely. The cold molecular gas, hydrogen in its molecular form, combined with carbon monoxide and other simple molecules, that constitutes the raw fuel for star formation. This gas emits and absorbs at radio wavelengths, and radio telescopes can map its distribution within distant galaxies, measuring how much fuel is available, how it is moving, whether it is concentrated toward the galaxy's center or spread throughout the disk. A galaxy that looks quiet in visible light may, at radio wavelengths, reveal enormous reservoirs of cold gas, enough to sustain star formation for hundreds of millions of years into the future. The fuel is there, waiting. The fire simply has not started yet. This is, in a sense, the great lesson of multi-wavelength astronomy. No single view of the universe tells the whole story. Visible light reveals stars and hot gas. Infrared reveals dust-obscured activity and cold structure. Radio reveals molecular gas and the signatures of jets. Ultraviolet reveals the hottest, youngest stars. X-rays reveal gas heated to millions of degrees and the radiation from actively feeding black holes. Each wavelength is a different language. Each one describes a different aspect of the same object. And only by combining all of them, by reading the full electromagnetic spectrum, from the longest radio waves to the shortest gamma rays, can astronomers begin to reconstruct the full, layered, complicated reality of a distant galaxy. It is, in a way, not unlike the way we come to understand a person. No single conversation, no single moment, no single view captures everything. Understanding accumulates slowly, from many different angles, over a long period of patient attention. And threading through all of this, the tool that makes it possible to arrange everything we see into a coherent history is redshift. When a galaxy's light reaches our telescopes, Its spectrum carries a signature of how far that light has traveled. The characteristic patterns of emission and absorption, the fingerprints of specific elements at specific wavelengths, are shifted toward the red end of the spectrum in proportion to how much the universe has expanded since that light was emitted. Measure the redshift, and you know the recession velocity. Know the recession velocity, and you know the distance. Know the distance, and you know how far back in time you are looking. It is a cosmic speedometer and a time machine simultaneously, a single measurement that places a galaxy precisely within the universe's long history. Low redshift means nearby. Recent. The universe roughly as it is now. High redshift means distant. Ancient. The universe as it was billions of years ago, when galaxies were younger and more chaotic, when quasars blazed more commonly, when mergers were more frequent, when everything was closer together and the story was still very much being written. By sorting galaxies by redshift, astronomers can arrange them into a timeline, a vast historical record of how galaxies have changed over the lifetime of the universe. From the clumpy, turbulent, starburst-lit systems of the early cosmos, through the great merging and quasar era of cosmic midlife, to the quieter, more settled galaxies of the present day. It is, in the end, a biography of the universe itself. Written in light. Measured in wavelengths. Read by patient instruments floating in the cold dark of space. And all of it, every quasar, every hidden starburst, every cold gas reservoir waiting to become stars, every jet carving its slow monument through intergalactic space, is out there right now. Continuing. Evolving. Indifferent to the lateness of the hour. You do not need to hold any of it in mind. Just let it exist, out there in the dark, while you rest here in the quiet. The universe is very good at continuing without any help from any of us. Close your eyes a little more. Let your breathing slow just a little further. Everything is as it should be. Let yourself arrive here gently. There is no rush. Just settle, slowly, into wherever you are, the weight of your body, the warmth around you, the soft darkness behind your eyes. We are near the end of our journey tonight. One final passage through the deep universe, and then you can let everything go completely. We have come a long way together. From the first light of the earliest galaxies, through the bending of space and the stretching of light, through collisions and mergers and the slow building of structure, through hidden starbursts and feeding black holes and the many wavelengths of a universe that speaks in more languages than we have instruments to hear. And now, in this last segment, we pull back. Further and further, until the individual galaxies grow small and the larger pattern they form becomes visible. Until we can see not just the trees, but the forest. Not just the galaxies, but the shape of everything. We begin with something we have touched on before, but which deserves a moment of quiet contemplation all its own. Every distant galaxy you have ever seen in an image, every spiral, every elliptical, every faint smudge in a deep field photograph, is a time capsule. Not metaphorically. Literally. The light leaving a galaxy 1 billion light-years away takes 1 billion years to reach us. And so the image we receive is not of that galaxy as it is now, but as it was 1 billion years ago. We are not seeing it. We are seeing its past. A snapshot, frozen at the moment of departure, carried faithfully across space for 1 billion years and delivered, intact, to our telescopes. This is true of everything we observe in the universe. The further away it is, the further back in time we are looking. There is no way to see a distant galaxy as it currently exists. By the time its light reaches us, the present moment has already moved on by millions or billions of years. Which leads to a quietly strange thought. Some of the galaxies we observe tonight, the ones whose ancient light is only now completing its journey to our instruments, may no longer exist in the form we see them. In the time it has taken their light to reach us, they may have merged with neighbors, their spiral arms disrupted, their gas consumed, their identities dissolved into something larger and unrecognizable. The galaxy we see is real. The light is real. But the object it describes may have transformed beyond recognition long before any human being ever existed to look for it. We are, in a sense, receiving letters from the dead. Messages sent by structures that have since changed utterly, arriving now, patient and faithful, as if no time had passed at all. The universe keeps its own records. It does not always tell us when things have changed. But the light, even as it ages, carries an extraordinary amount of information. And one of the richest sources of that information is the spectrum. When the light from a distant galaxy is spread out by wavelength, separated into its component colors, the way a prism separates white light into a rainbow, it reveals a pattern of bright and dark lines. Bright lines where specific elements are emitting radiation. Dark lines where specific elements are absorbing it. Each element has its own unique pattern of lines, as distinctive as a fingerprint, as readable as a barcode. From these spectral lines, astronomers can determine what elements are present in the galaxy's stars and gas. They can measure the temperature of the gas. They can detect whether the gas is moving toward us or away from us, and how fast, from the way the lines are shifted. They can identify whether the galaxy is forming stars actively or quietly winding down. All of this, from light. From the careful analysis of which wavelengths are bright and which are dark, in a signal that may have been traveling for billions of years before it arrived. And one of the things that spectra reveal, when we look at the earliest galaxies, is a kind of elemental poverty. The ancient universe had not yet had time to build the periodic table we know today. The first galaxies formed from hydrogen and helium, with only the faintest traces of anything heavier. And their spectra show this. When astronomers measure what is called metallicity, the abundance of elements heavier than helium, which astronomers collectively and somewhat loosely call metals, early galaxies come up low. Sparse. Elementally simple. This is not a deficiency, exactly. It is youth. The heavy elements had not yet been forged. The generations of stars that would build them, live out their lives, and scatter their products across the galaxy had not yet completed their work. With each passing billion years, the metallicity of galaxies rises. More generations of stars live and die. More supernovae scatter their newly forged elements into the interstellar medium. More of those elements are incorporated into the next generation of stars, and the next, and the next. The universe slowly enriches itself, building, element by element, the chemical complexity that makes planets and oceans and living things possible. We are, in the most literal sense, the product of that enrichment. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged inside a star that lived and died before the sun existed. The universe built you slowly, across billions of years, one supernova at a time. But those supernovae do not only enrich galaxies. In small galaxies, they can also damage them. When a massive star explodes at the end of its life, it releases an enormous amount of energy, enough, in a small galaxy, to drive powerful winds of gas outward from the galaxy's center. In large galaxies, gravity is strong enough to hold most of this gas in place. But small galaxies, with their shallower gravitational wells, can lose significant amounts of gas to these supernova-driven winds. Gas that was destined to become future stars is instead blown outward, not into the galaxy's disk, but into intergalactic space, carried out along the tendrils of the cosmic web, enriching the vast emptiness between galaxies with the metals that supernovae created. It slows the small galaxy's growth. It limits its future. But the gas does not disappear. It joins the larger reservoir of the intergalactic medium, enriching it, preparing it, making it available, perhaps, for future generations of structure that have not yet begun to form. Nothing is wasted. The universe has very long plans. And now, let us pull back. Further than we have gone before. Until individual galaxies are no longer the focus, but the texture of something much larger. On the very largest scales, scales of hundreds of millions of light-years, galaxies are not distributed randomly through space. They are not scattered like dust shaken from a cloth, falling where chance dictates. They are arranged, organized into a structure so vast and so intricate that it has its own name. The cosmic web. Galaxies cluster together along long, thin filaments, threads of matter stretching across tens or hundreds of millions of light-years, where the density of gas and dark matter is slightly higher than average, and where gravity has, over billions of years, drawn galaxies together into chains and sheets. Where filaments intersect, great clusters of galaxies form, the densest, most massive structures in the universe, containing thousands of galaxies bound together by their mutual gravity. And between the filaments, between the clusters, between the sheets and walls of galaxies, vast voids. Empty regions of space, hundreds of millions of light-years across, where almost nothing lives. Where the density of matter is so low that very few galaxies have ever formed, and those that have tend to be small and isolated and quiet. The cosmic web looks, in simulations and in survey maps, remarkably like something biological. Like a neural network, or the mycelium of a fungus, or the fine structure of a soap bubble. Thin strands enclosing great empty spaces, meeting at bright nodes, forming a pattern that repeats across all the scales we can observe. It is the largest thing in the universe. Larger than clusters, larger than superclusters, larger than any structure with a name that most people have ever heard. And the galaxies within it, each one containing hundreds of billions of stars, are just the visible markers, the lit points, tracing the skeleton of something made mostly of things we cannot see. That invisible something is dark matter. We cannot observe dark matter directly. It emits no light. It absorbs no light. It interacts with ordinary matter only through gravity. But its gravitational effects are unmistakable, and without it, the universe as we know it could not exist. Dark matter forms vast halos around galaxies, invisible, extended structures of mass that outweigh the visible stars and gas by factors of 5 or 10 or more. These halos were the first structures to form in the early universe, collapsing under their own gravity before visible matter had time to cool and condense. And it was into these dark matter halos that gas eventually fell, forming the first stars and galaxies in the deepest wells of invisible gravitational potential. Dark matter is the scaffolding, the framework on which everything visible is built. Without it, galaxies would not have formed where they did, or when they did, or in the numbers they did. The cosmic web itself, that vast, beautiful, biological-looking structure, is, at its core, a map of dark matter. One of the earliest clues that something like dark matter must exist came from watching galaxies spin. When astronomers measured the rotation of spiral galaxies, tracking how fast stars and gas at different distances from the center were moving, they found something that could not be explained by the visible mass alone. In a galaxy where most of the mass is concentrated in the bright central bulge, physics predicts that stars in the outer regions should orbit more slowly, just as the outer planets of our solar system move more slowly than the inner ones. But they do not. The outer regions of spiral galaxies rotate at roughly the same speed as the inner regions, or even faster. The rotation curves, graphs of orbital speed versus distance from the center, remain stubbornly flat where they should fall off. The only explanation consistent with the data is that there is far more mass in these galaxies than is visible. Mass spread out in a large, extended halo, invisible, but gravitationally present, holding the outer stars in their orbits, refusing to let the rotation curve fall. Dark matter, hiding in plain sight, revealed by the motion of stars that should not be moving as fast as they are. And the universe, it turns out, has preserved within itself the echoes of its own earliest moments. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma, gas and light coupled together, with pressure waves moving through it like sound waves moving through air. These waves had a characteristic scale, set by the speed of sound in that early plasma and the age of the universe at the time they froze. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, the light and gas decoupled. The pressure waves stopped. And their final positions, the scale at which they froze, was imprinted permanently in the distribution of matter throughout the universe. These frozen echoes are called baryon acoustic oscillations, and they are visible, subtly, in the large-scale distribution of galaxies. There is a slight preference for galaxies to be separated by a specific distance, the distance set by those ancient sound waves, written into the galaxy surveys that astronomers have built over decades of patient observation. It is one of the most extraordinary things in science. A sound wave from the first few 100,000 years of the universe's existence, its final position preserved for nearly 14 billion years, readable in the statistical patterns of galaxies spread across hundreds of millions of light-years of modern space. The universe remembers. Even across distances and timescales that erase almost everything else, certain patterns persist. And so, modern astronomy turns all of this, the redshifts and the spectra, the rotation curves and the clustering patterns, the acoustic oscillations and the positions of millions of galaxies mapped across the sky, into something larger still. A measurement of the universe itself. By studying how galaxies are distributed, how they are moving, how their light has been stretched by the expansion of space, astronomers can measure how fast the universe is expanding, how that expansion rate has changed over time, and what the universe is made of: ordinary matter, dark matter, and the mysterious dark energy that appears to be accelerating the expansion of space itself. Individual galaxies, in this context, become data points. Each one a probe, a measurement, a small piece of evidence contributing to a picture that none of them could provide alone. Billions of galaxies, each one a candle in the dark, and from the pattern of their light, their distances, their velocities, their clustering, the shape and fate of the entire universe slowly becomes legible. It is, perhaps, the grandest use to which light has ever been put. And now we are here, at the end of our journey. having traveled from the first light of the infant universe to the largest structures space contains. Having passed through ancient galaxies and gravitational lenses, through mergers and quasars and hidden starbursts, through invisible scaffolding and frozen sound waves and the slow, patient work of telescopes listening across every wavelength. The universe is vast. It is old. It is stranger and richer and more intricately structured than any of us can fully hold in mind. And it is, in the end, made of the same things you are, the same atoms, forged in the same stellar furnaces, scattered by the same ancient explosions, assembled by the same patient gravity. You are not separate from what you have been contemplating tonight. You are part of it. A small, warm, temporary arrangement of the universe's own material, lying still in the dark, looking back at where it all came from. There is nothing more to think about now. Let the cosmic web hold its shape without you. Let the galaxies continue their long, slow work. Let the ancient light keep arriving, patient and faithful, at telescopes that will still be watching long after tonight is over. You have traveled far enough. Rest now. Let everything go. Sleep well.